So thanks again. So I mean, before continuing, I would like to say a few things in a more precise way. So I realized that yesterday I was a bit sloppy when, for instance, I define equilibration. Okay, because I say that we can say that a system equilibrates. Okay, if you do some dynamics, so you have some unitary dynamics, you have a system, and then you look at a portion A of it, and then you say that the system equilibrates if there is this if this limit exists. Okay, if rho A of t converges at t equal infinity to some rho A infinity. Okay, so but when you for this limit, so you have to be careful because so there is a precise order of limits that we are considering. So first the thermodynamic limit, okay, then you take the infinite time limit, okay. So you let the reduced density matrix of A reach some equilibration, and then if you want to make a statement about the fact that the system thermalizes or equilibrates to a GG, you have eventually you take the limit small l to infinity. Okay, so if you try to compare, let's say, the reduced density matrix, for instance, the von Neumann entropy computed from the reduced density matrix with some entropy that you compute from one of these ensemble, this you have to take the limit in which the size of A goes to infinity. But the limits have to be taken in this precise order. Okay? This will become clear when we will write down the quasi-practical picture for the von Neumann entropy, and we will see in which regime the quasi-practical picture will hold. Okay. So I mean, yesterday, so I finished introducing this ensemble, so the Gibbs ensemble and the GGE. So again, chaotic dynamics are believed to lead to thermalization, with exceptions, of course, which means that local properties in the steady state, they are described by some Gibbs ensemble, which depends only on the energy, density, or inverse temperature. Okay. On the other hand, if the system is integrable, there is an extensive number of conserved quantities, which are local or quasi-local. Okay, again. Or quasi-local. Okay. They strongly constrain the dynamics, and as a result, you cannot use the Gibbs ensemble. You have to somehow can generalize it, introducing these extra Lagrange multipliers. Each Lagrange multiplier is fixed by demanding that the steady state expectation value, the ensemble expectation value of a conserved quantity is equal to their initial value, because the expectation values of all these IM are preserved during the dynamics. Okay. Now I wanted to mention briefly. I want you, to view this from the perspective of ETH. Okay. So because indeed these ensembles, both the Gibbs and the GG, can be thought of emerging from some ETH or generalized ETH. Okay. So let's imagine of having the many-body energy spectrum, okay, of the Hamiltonian H, that we use to drive the dynamics. Okay. So what is the statement of ETH? So first of all, let's say, for instance, for lattice models, it's clear that the gap between, this delta E, which is the gap between nearby energy levels, it goes as e to the minus L. Okay, it's exponentially decreasing as you increase the the system size. Okay. This means that if you take a macrocanonical energy window, okay, what will happen is that in this macrocanonical energy window, what will happen is that in the thermodynamic limit, there will be an exponentially diverging number of energy levels. Okay. Now, the statement of ETH is that essentially all eigenstates in the this microcanonical window are thermal. Okay, so this means that, and of course the thermal with the the corresponding energy around which you put the energy, the macrocanonical energy window. Okay, so this is a conjecture. It's called the ETH conjecture. Okay. So it is supported by exact analyzation studies. Okay, you can do exact analyzation even though you are limited to small system sizes, and you can actually verify this. Okay.
What do you mean by eigenstate being thermal?
It means that if you compute the eigenstate expectation value this, okay, for some eigenstate n, which lives here, okay, this eigenstate expectation value for generic local observable will be the thermal expectation value. Okay, will be trace of okay. And all the eigenstates in this energy window will give the same expectation value with exceptions. Well, exceptions. Yeah, it's not clear if there are exceptions at all, actually, if the model is chaotic. Okay. Now, what happens if you have integrability? So, if you have integrability, a lot of things go through in the sense that let's repeat the experiment now with an integrable model. Okay, so let's fix some energy window, take the eigenstates. Imagine we can do it. Okay, and then if we pick at random the eigenstates, what will happen is that this will be still true. Okay, this sounds surprising, no? Because you would imagine that integrability is associated with the violations of thermalization. So okay, what is the explanation? The explanation is that despite integrability, the explanation is that there are fluctuations, a lot of more fluctuations in this macrocanonical window. So if you take eigenstates at random with the probability almost 1, you pick a thermal state. But then you can ask, are there non-thermal states in this microcanonical window? And the answer is yes. Actually, there is, again, an exponentially diverging number of non-thermal states as you take L to infinity. Okay? So integrability means that, I hope I'm not saying wrong things, but in the macrocanonical window, there is an I don't think so, an exponentially diverging number of non-thermal states. Okay? Right? The reason why, if you, yes?
Exponentially
diverging with L, okay? With system size, okay? The reason why, if you pick eigenstates at random, you get thermal eigenstates is because the ratio between non-thermal versus number of thermal goes to 0 when L goes to infinity. Okay? What does it mean? It means that, let's say you have this goes as e to the alpha L. This goes to the beta L. If beta is larger than alpha, then even though the both numbers grow exponentially, the ratio goes to 0. What are alpha and beta? What is alpha and beta are the thermodynamic entropies, okay? So alpha and beta, this is essentially the thermodynamic entropy. I mean, let's put it here. So this number goes as e to the density of thermodynamic entropy at the given energy E times L. This number, okay, so let's do something even more, which looks more constraining. Let's, in the microconical window, choose the eigenstates that have some desired expectation value for these conserved quantities, okay? This would define a GG. And this number here goes as e to the well, with the fixed number of, okay? Is that clear? Now, it's clear that the entropy of the GG is larger than the entropy of the thermal ensemble because here you're putting more constraints. Here you're just fixing the energy. Here you're fixing a lot of more things. So it's clear that you have fewer eigenstates, okay? What are the implications of this? The implication of this is that even if you take an integrable model, if you are not careful enough in choosing the initial state, might be that you select only thermal eigenstates, okay, that are relevant for the dynamics. So, I mean, even in integrable systems, if you don't choose carefully the initial state, you can thermalize. Okay? The point is that in integrable systems, you have a lot of opportunities to violate thermalization because you have these non-thermal eigenstates in the middle of the spectrum. So if your initial state somehow is chosen with, I mean, if you're careful in choosing the initial state, you might have significant overlap only with these non-thermal states, okay? And then this implies that instead of a thermal ensemble, you end up with some GG, okay? Is that clear?
One question.
Yeah.
So when we are considering ETH in chaotic systems,
Yeah.
is there any so given the whole spectrum, is there any specific place where we should choose the microcanonical?
I mean, yeah, you have to stay away from the boundaries of the spectrum. But as long as you have a finite energy density, it should work well, okay? So you have to choose, you have to choose the energy such that, you have to stay away from the boundaries, okay? Ground states or, if you're in a lattice model, then of course you have some bounded spectrum, you have to stay away from the edges. Okay? But at finite energy density, this is believed to be true.
Sorry, question?
Yeah?
Is there any other way to characterize these non-thermal states than by the fact that the local operator one function is not thermal?
Yeah, actually, I think that the difference is quantitative. Okay,
So it's not like they have different, I don't know, different
No, no, no. They have extensive. So here at this level, yeah, okay, good point. So I could compute the entanglement entropy for each of these eigenstates. I could, let's say, isolate a portion A and then compute the entanglement entropy. They would always have volume law entropy. Okay, in the middle of the spectrum of integrable systems, actually even high in the energy, you can construct states that have a log entropy. Okay, but this the number of these states. This is a different story. Okay, the number of these states actually is suppressed. It's not thermodynamically relevant. Okay. To have thermodynamics here, you need to have a number of, an exponentially diverging number of states, because this means that you are at finite entropy. So there are other states which violate, which are even more special in the sense that they don't have extensive entropy, but at the same time their number is they are negligible. It is thermodynamically negligible. This happens actually even in non-integrable systems. So there is something called quantum scarce, and quantum scarce. What does it mean? It means that in the bulk of the spectrum, you have some states that are special. They don't have, they don't have volume law entropy. And then, if your initial state is overlapping a lot with this, then in the dynamics, they give some exotic behavior. Okay. Okay. Now the question that I would like to slowly approach is there a signature of these quantities, of these GGE quantities, so for instance of the thermodynamic entropy of the GGE, in the dynamics of the entanglement entropy, okay? Yeah. Actually, I mentioned at the end of the last lecture that there is a deep intertwinement between GG and entanglement dynamics. So I can anticipate that in several cases, what will happen is that the growth of the entanglement entropy will be described in terms of this thermodynamic entropy of the GG. Okay. But okay, now today, at least in the first hour, what I want to do, so let me get to the point. Where is it? So today the plan is that in the first hour, I sketch for you the derivation of how you derive the quasi-practical picture in conformal field theories. Because, okay, even though it's a bit technical, I think you can at least grasp the gist of it. And this will allow me to introduce the main formula that then appropriately modify will give the quasi-practical picture for generic integrable models, both free and interacting. Okay. So essentially here so this of course is not my work. So this has been done by Calabrese and Carty, by now some classic papers, okay, 2005. Just to Google it, you can find everything. So the starting point is to get path integral representation for the density, for a density matrix, okay? For density matrix, okay? We consider a field theory And then we try to write the density matrix, okay? So let us consider a bosonic field theory, okay? So we'll have some bosonic fields, phi, okay? Okay, to live in each point of space, okay? Now, I mean, if you're not too comfortable with fields, you can always imagine of discretizing everything and going back to some lattice model. This is the way I do. Okay, so we can start by defining a density matrix. Density matrix, rho, will be an object that will have some indices, okay? Will depend on the field configurations. Okay? At some positions x and x prime. Okay, this you can imagine of being the row and column indices of the density matrix. Okay. Again, if this is confusing, you can think of spins. Okay, and this will be the spin configurations.
Is it just functional?
What?
Is it just functional of phi? That's all?
Yeah. Okay. You want to be sure. This is just, so now let us consider some finite temperature seconds, beta h, then phi prime, okay? And the z is, of course, the trace. Okay? So you see that, I mean, if you send beta to infinity, essentially what you do, you select the ground state of your model, and then this would be the ground state density matrix. Okay? Okay? Then, I mean, you can represent this as a path integral, as usual. No? So you can write rho as z minus 1. Then you have to integrate over your fields. Okay? Then you have to put some deltas to fix x prime, product of x, delta phi x beta minus phi second x second. Now I'll explain what I'm writing. So times e to the minus the SE, which is the Euclidean action. Okay. This is the usual thing you do. So you have this object. Then in the path integral, it gives you the Euclidean action. Okay. So SE is integral from 0 to beta, the Euclidean Lagrangian theta. Okay. I'm considering finite beta. Okay. Now this is the path integral, and here these deltas are to put this. I mean, to fix this this condition at tau equals 0 and tau equal beta. Okay? So what is this? I mean, pictorially, this is doing the so you have your 0 beta. Then here you have your configurations phi prime x prime, phi second x second. Okay. Then this is the tau, imaginary time. And then you are doing the integral here, okay, in this region. Okay? Along the spatial direction, you can think of the system being infinite. You can also, if you want, put boundary conditions. Okay? Periodic boundary conditions. Okay? Now, this is convenient as many other pictorial representations. So how do we represent the reduced density matrix now in this language? So we represent it by tracing over degrees of freedom that are outside of a certain region. Okay? So let's say that we consider region A here. Sorry, here I put it on the other side, region A, okay, which corresponds to some line here. Then we have to trace over the rest, which means that tracing means that we identify the field configurations on this region, and then we integrate over. Okay? This would be rho A. Okay? Okay? So, it's clear? We can actually do something more. So we can compute. Let me do it here. So we can compute the moments, so trace of rho A to the n. So we can compute all the moments of the reduced density matrix. If we have all the moments, we can compute also the von Neumann entropy by, I'll tell you how, but this is essentially the replica trick, okay? Then via the, this is the replica trick, okay? Replica trick, you can compute SA, S of rho A, where S is the von Neumann entropy, okay? So how do we compute this? So this actually pictorially is clear, no? Now my drawing abilities are seriously challenged, but let me do it. So what we have to do is, so we have, let's say that we fix n to 2, okay? N equal 2. Then n to 2 means that we have to take two copies of this object. So let's put one here, and again. Well, it's not very nice, but it's even less nice, but anyway. Sorry. And then, okay, let's remember that at some point here, so you see when we defined rho A, we integrated here, but we left, sorry, here imagine that this is, no, sorry, yeah, okay. And here we left these indices not fixed, okay? So this means that we have a surface like this where, fields on the two edges are identified, okay, and are integrated over. But then along this slit, which corresponds to my subregion A, then here I have my phi, and here I have my phi prime and phi second. Okay? So along the slit, on the two sides of the slit, I have the two fields configurations, phi prime. And here I have the same, okay? This is the second copy. Now, if I want to take rho square, so I have to, again, contract row indices with the column indices, which means, let's say, if this is row index on the lower part of the slit, and this is the column index, which means that I have to take I have to identify the fields here with the fields here, and then to take the trace, I have to identify the fields here, and here, okay? Like this, and oops, like this. Okay. Okay. It has some beauty, but okay. So what do we get? Essentially, we get that computing this rho a to the power 2, trace of rho a to the power 2, is equivalent to computing a partition function, okay, of your theory, not on the plane or on this object here, but on a complicated object, which is actually a two-sheet Riemann surface, okay? This is essentially the two-sheet Riemann surface, okay? If you want to compute trace of rho a to the n, you have to go to n sheets, okay? And it's clear how they are connected, right, in the usual way. I mean, this, you easily generalize this. So in the end, so in the end, what we get is that, I mean, trace of rho a to the n is equal to actually a ratio of partition functions, because of course rho a is normalized with 1 over z, where this zn is n-sheet Riemann surface, and the other one is just the plane partition function to the power n. Okay. Now here we have to make a jump, because I mean I cannot explain you conformal field theory in just 10 minutes, but so what you can argue, what you can show actually, is that this ratio of partition functions, I mean, instead of working with n-sheet Riemann surface, you can actually is the expectation value of some weird operators on the plane. Okay. So you can represent this, you can compute this ratio by expectation values on the plane, okay, not anymore on the Riemann surface, of some appropriately defined, if you want, operators, which are called twist fields, okay? These Tn are twist fields, okay? Actually, the T is the twist, and T tilde or bar is the anti-twist. So what they do essentially is when you insert them, they create a branch cut, okay? And this branch cut somehow, gives you the Riemann surface. Okay. Then the other thing that you have to show is you would like to know some properties of these twist fields, and then actually you can show that these fields, in the language of CFT, in the framework or whatever, Tn behave as primary operators. Okay. And they have some scaling dimensions, delta n, which are C over 24 and 1 minus n. Okay? These are scaling dimensions of these twist fields. Okay? And the C is the central, is the famous central charge. It's the famous central charge. Okay. So they are primary operator, means that they behave nicely under conformal transformations. Okay. And the scaling dimensions are this object here. Okay. So if you have a primary operator and then you know the scaling dimensions, essentially you know its two-point function. Okay. So this means that Zn, this is equal to Tn u T bar n v on the plane. Sorry, this u and v are, yeah, I should have said that these twist fields are inserted at the boundaries of your subsystem, okay? And u and v are just the points at which you insert these fields, okay? Now, I understand that this is a bit abstract, and yeah, I mean, not all of you know CFT, but so, I mean, the important thing is that if you are able to map this object to a two-point function and you know the scaling dimensions of the operators that you have there, then the two-point function is fixed, because any two-point function will behave as some constant, Cn, and then v minus u to minus 4 delta n. So it always goes like this, okay? So if you have the scaling dimensions of the operators, then the two-point function decays with some exponent where these scaling dimensions appear, okay? So this is the only thing you need. Now, someone told you the scaling dimensions. This means that you can put here, this goes as C over 6 n minus n, okay? Okay. Now, for those of you who know, we are one step from showing that the entanglement entropy grows logarithmically in the ground state of a critical model. But what we want to do now is to change a bit. So this is just if you want an introduction, the introductory part. So we would like to attack the quench problem with this machinery. Okay? Now, what happens in a quench? So and this, again, is another classic binaural calculation. So even though I'm confident that if you don't understand the details, you still somehow things remain in your mind, and one day you will you will understand. Okay, so let's consider the wave function, the evolved wave function, so psi of t, which is e to the minus I h t sum psi 0. Okay. Now, so if you know CFT, I mean, if you are Giancarlo or Pasquale, then you realize that here what you have to do is actually you have to put some, sorry, this is, I mean, first row is clear, no? It's just the evolution of a state from some initial state. To make things converging, you have to add a regulator. So this is a regulator. you need it to make things converging, okay? Now, so what we would like to do would be to exploit again go to imaginary time and write this object as a partition function, okay? So in order to do that, what I'm going to do now is to consider tau equal to IT, okay? Go to imaginary time, so epsilon now appears in the same way as tau, okay? Then this, and then in the end, eventually, we will remember that tau has to be continued analytically, okay? Okay, so this means that here, so let's now write this, the density matrix again. The density matrix now is tau minus epsilon h, sorry, tau h minus epsilon h, then psi 0 e to the tau h minus epsilon h. Then psi prime, okay? Where again, second, the psi prime label the entries are the row column indices of row, okay? These are the matrix elements of row, okay? And now you see, instead of IT, I have tau, okay? Now, now what I want to do is again to, now disappeared, but take this expression here and imagine, draw the corresponding pictorial representation. So this is equal, so to this thing here. So let me get it correct. Zero, and then this is minus epsilon. This is epsilon. This is tau. Okay. So you see this thing here. So you see the total imaginary time travel here is tau plus epsilon. And this corresponds to this term. On the other side, you evolve psi 1 by epsilon minus tau. Okay? So you do the path integral here. And then you have a psi 0. Psi 0 is boundary conditions at minus epsilon and epsilon. And here you have your field psi prime. Okay? Now, you can introduce your subsystem because you want to you want to trace you have to compute the reduced density matrix, so you can imagine of putting your subsystem A here, and this introduces some, again, some slit, okay? Now, this would be rho A, sorry. Because now if you put the slit, it's rho A. So again, you would have to compute, sorry, this is, of course, we work in CFT, so this is the complex plane, okay, W. And here I have this point here correspond to imaginary part of W equal tau, and here imaginary part of W equal epsilon. Now you will get confused because we have the imaginary part of W, which is tau, which was complex. But this is the main point where one gets confused here. Okay, but now the point is that you have to compute the partition function on this weird strip. This is a strip, you see, of width 2 epsilon, with this slit. This is complicated. Because you have two boundaries, you have a slit in between, it's very complicated. But you can, so first of all, you can remember that having the slit here corresponds to putting some twist fields at these boundaries here. Okay? And then to simplify this, you can map to the upper half plane, okay, via conformal transformation, okay? There is a conformal transformation which is you go from W to Z, which is equal e to the pi over 2 epsilon W, okay? If you apply this conformal transformation, you map this geometry into the upper half plane, okay? Upper half plane, where things are somehow easier. It's easier to compute a correlation function in the upper half plane where you have just one boundary rather than in this weird strip, okay? And here in the upper half plane, you have this point Z1 and Z2, which are the two endpoints of your interval, okay? So Z1 actually is e to the I pi tau over 2 epsilon, and Z2 is equal to e to the L pi over 2 epsilon plus I pi tau over 2 epsilon. Okay? L, again, L is the length of the subsystem. Okay, now we are almost there. So let me see. Yes, I think I can make it. So now the problem is you have a CFT with the boundary, and you have two fields, twist fields inserted here, and the anti-twist field here. How you compute this in CFT? This looks more like a textbook. Okay? If you open the yellow book, there's a problem there's a ticket with a boundary, so it's not so trivial. But essentially, this resembles a 4-point function of the operators, because you have a boundary, so it's like having images of the operators. Okay? So,
Can I ask a question?
yeah.
So the boundaries on the left side, where are they mapped to on the right? Because you're saying it's simpler, you only have one boundary, but what happened? How are they mapped?
Well, yeah, I don't remember, but I think they go here and here. It's like opening, I think. But you can check it yourself by doing the transformation.
And are you also thinking of completing the row to some power again?
Yes. But yes. Yeah, again. Yeah, but the row to some power. I'm cheating a bit, okay? But the row to some power because I map the n-sheeted Riemann surface in the plane in the previous case. Here, the n-sheeted Riemann surface is mapped into this half plane, if you want. Okay. So what I have to compute now is Tn of Z1, T bar n of Z2 in the upper half plane. Okay. And this, then you have to believe me. So this is Z1 2 bar, Z2 1 bar over Z1 2, Z 1 bar 2 bar, Z1 1 bar, Z2 2 bar to the power 2 delta n. Delta n is, again, the scaling dimensions of the fields. And then, in principle, you would have a function f of this eta, and eta is the cross ratio, okay? Okay? The cross ratio, for those of you who know, in CFT is a combination of this z that is invariant under global transformations, okay?
Excuse me, what the bar?
Yes, and the bar, so here, so Z12 is equal to Z1 minus Z2. And you put the bar means complex conjugation. So 2 bar, for instance, means that you complex conjugate the Z2. Okay? Okay? Okay. Now almost there. Yes, so there will be this function of eta, but in this case, so we are interested in the limit L t much larger than epsilon, okay? And on top of that, here at the end we will send tau to it, and in this limit, this function essentially becomes a number, okay? So it doesn't matter too much for the scaling, okay? So this actually very, I mean, as you know, this is as the structure of a four-point function of a primer operator in CFT, and as you know, this is the general behavior. So you have something that is algebraic here, and then you have some function, which actually in general is very interesting. So if you compute this function in ground states in the vacuum of CFT, you can compare with the calculations in the ground state of of models that describe conformal field theory, and then you can match them because this function is universal, okay? It's very nice. It contains all information about CFT because it depends on partition functions essentially. So it has all the universal information that you can have in a CFT. Okay? Okay. Now there is a last thing that we should do because we didn't take into account the effect of the transformation, the exponential. This would add another factor here, but I mean, essentially, you have to multiply by, so you have to multiply by, so let me write it here. You would have to multiply by the Jacobian of the transformation, sorry, Z1, as usual to the scaling dimensions, okay? Minus 2 delta n, okay? This is just because we are doing the conformal mapping. The conformal mapping, when you have a primary operator, it gives you some, of course. Yeah. But let me in the end show what we get. So after doing all the algebra and taking, which means also sending tau to it, and then considering LT much larger than epsilon, then we can show that trace of rho a to the n is proportional to e to the pi L over 2 epsilon plus e to the pi t over epsilon divided by e to the pi L over epsilon times e to the pi t over epsilon to the power 2 delta n. We get this. Sorry, now, okay, we neglected some terms here because we took this limit, but we can do a little bit better. Well, actually, we did everything we could, I think, up to now, but okay. Now, okay, we have this. We have to compute the Renyi entropies, I mean, something which is called Renyi entropy, which is 1 minus n, trace of rho a to power n, okay? It's just amount, logarithm of trace of rho a to power n, okay? Simple, we have to take the log of this, which brings down this 2 delta n, we divide it by 1 divided by 1 minus n, and then if we send n to 1, we get the von Neumann, okay? It's just, again, simple algebra. We imagine of doing it. And we get to some beautiful, because simple, get to some beautiful result. So I'm almost done, okay? So in the end, we get to, so we get to this result. So SA is equal to minus C over 6 logarithm of e to the pi L over 2 epsilon plus e to the pi t over epsilon divided by e to the pi L over 2 epsilon e to the pi t over epsilon. Okay? Now again, you see that there are two cases to distinguish. So SA of t so if L is larger than 2t, okay, you can choose only, I mean, you have two exponentials, but one of them is dominating, okay? And then this means that here you get p pi over 6 epsilon t if t is smaller than L half. Otherwise, I forgot the c here, p, c, 12 epsilon L if t is larger than L half. This is the final result, okay? So, which means that if you plot the von Neumann entropy as a function of time, then it has a linear growth, and then it saturates, okay? Where this point here is t equal L half, and this is some function of time, okay? So in a generic conformal field theory, we see that the entanglement entropy linearly grows with time at early times, and then after times of the order of L half, then it flat. And this has some qualitative features that you observe, let's say, in numerics. Yes, this linear growth is seen in numerics. Now, in the next hour, I will give a quasi-particle interpretation of this formula, and then I will start heavily computing to show this formula in a microscopic model, okay? Yeah, see you after the break.
Thank you very much. Are there questions?
Can you give an example of thermalization in integrable classical system? Can you say that?
I mean, I can give you an example in integrable quantum.
There is no analogy completely classical and quantum integrable system.
This is a good question. Maybe in the classical system, it would correspond to choosing some initial conditions, right? This is what I would expect. Maybe, I don't know, but...
Yeah, I think that integrable system in classical physics is just integrable. It doesn't thermalize.
But I mean, at the quantum level, for instance, even if you take, let's say, an XXZ spin chain or an Heisenberg spin chain, which is the prototypical integrable spin model, if you start, let's say, from a product state that has as random up and downs, I think you expect this should lead to thermal behavior. Maybe there is a simpler choice. Let's say that you have XXZ, which is, okay, so it's a spin model, spin 1/2 model, and then you start from some random up and down state. I think this you can show that it will be thermal. So again, as I was stressing it depends on the initial state that you choose. So, but the system is integrable means that you have actually, I mean, a fairly large number of initial states for which you violate thermalization, okay?
Maybe just a small comment. In classical systems, you can have integrable systems with unstable saddle points, and only for those unstable saddle points you can have positive Lyapunov exponents.
You see,
there
yeah.
are some trajectories which will be chaotic trajectories, but
Yeah.
only at the unstable.
Yeah, which means that you should choose the initial condition maybe carefully, so you can.
Even a simple harmonic simple.
I'm not an expert on classical. Yeah.
Positive Lyapunov exponent.
Okay.
But usually they are not considered when we say this chaos in integrable systems.
Okay.
Those are kind of
That's an interesting question, but yeah, I don't know. Okay.
I may ask, you mentioned the CFTs which appear here with some central charges. Is
Yeah.
there some specific class of CFTs that you consider, or which appear in the problems which are of interest? Are there some constraints on C?
No, I mean here, no, at this level, no. I mean, no. I mean, of course, yeah. I mean, calculations, for instance, in a DSCFT would give some violations of this. But actually, at this level, they coincide because, I mean, this linear plus saturation growth is kind of universal. But if you consider some DSCFTs, I think you can, at subleading level, there are differences, okay? So, for instance, if the mutual information can have very different behavior, okay? But I think at the level of entanglement entropy, you always get this linear plus saturation. So another thing that I should mention is that, I mean, so the question that we should ask at this point is, how much does this formula give us, okay? So I mean, this formula predicts that the prefactor of the linear growth is related to the central charge. Then, of course, you see it depends on the regulator.
I'm asking central charge of what?
Of the CFT, of course, yeah.
Which CFT? How do you identify it? How do you know? I mean, can you say precisely which CFT you have?
When you do, I mean, this can be, I mean, say Ising or a boson, whatever, right?
I ask what kind
Yeah.
of CFT?
I mean, Ising, boson, all the ones we know, but minimal models, whatever. But okay, the reason maybe because why I'm not stressing it too much is that this, what we should take out of this formula is that there is the linear growth, and then eventually there is saturation. But then if you want to compare with the macroscopic model, the comparison is not easy to make, because when you do the out-of-equilibrium dynamics, you probe parts of the spectrum which are beyond the CFT description. So the CFT description, if you take a lattice model that has a critical ground state, it applies to the ground state, so which means the vacuum of the CFT, and also, I mean, few excitations above it. But when you do the dynamics, when you do a quench, you are pumping, you are going very far away from this regime. So if you do a quench in a lattice model, so, I mean, we will not see this, okay? We will see some linear growth at early times, some dependence on some, and then some saturation, but this will be somehow slowed down because you have the higher part of the spectrum. So you don't have a linear dispersion of